Hello, and welcome to today's Laser Focus World webinar, High Power Laser Measurement Challenges and Solutions, presented by Endeavor Business Media and sponsored by MKS Ophir. I'm Justine Murphy, an editor with Laser Focus World and Multimedia Director of Endeavor Business Media's Digital Infrastructure Group. We welcome your questions during the webinar. They'll be addressed during a Q&A session following the main presentation. You can send them at any time by using the Ask a Question box, and we'll answer as many of those questions as possible during that Q&A session. If you have any technical difficulties, just use that same Ask a Question box, and our webinar team will be happy to assist you. And we recommend disabling any pop-up blocking software or extensions in your browser because these can cause issues with the webinar player. And if you need a better view of the event, just click the upper right of the presentation and media player window to expand them. Please be aware that today's presentation is being recorded and will be available on the Laser Focus World website within the next 24 hours, and you'll be notified by email when that's ready. You can also refer a colleague to today's discussion, share it on social media, or access event resources by clicking the icons on the left side rail of your screen. And we encourage you to stay until the end of the webinar for an exit survey, which will pop up on the screen. You can preview the questions ahead of time by clicking the exit survey icon on the left side rail. And now let's meet today's speaker, Mark Slutzki, Product Manager for Power and Energy Measurement Solutions at MKS Ophir. With a degree in electro-optics and applied physics, he has had many years of experience in the field, including as a research physicist for the Israeli Air Force. Hello, Mark. It's great to have you here. The floor is yours.
Okay, thank you. It's great to be here, and thank you, everybody, for joining us. I appreciate the time that you're taking. I just have to mention, I was having some technical glitches earlier. Justine, I now see that the next button seems to be active, so I'm going to try using that, and if it doesn't work, we'll go back to having you roll the slides forward. Let's just see if that works. Yes, okay, good. May all technical glitches be solved as easily. All right, so again, thanks for joining us. The topic that we're going to be discussing is a very important topic in my eyes. Well, let me just go back to this slide. The sort of measurement instruments that we're talking about here, which are used in advanced, sophisticated applications, are by necessity themselves advanced and sophisticated, and if I may say so, relatively expensive. After helping so many customers deal with avoidable problems, we felt it would be an important contribution to the industry if we could offer helpful information so that users of such instruments can get the best performance out of them and the longest lifetime. I tried to keep the information as generic as possible so that it'll be as helpful as possible to as many of you as possible. With that, I'll just mention that when I'll be using specific examples of actual instruments, then as you can appreciate, I'll be using Ophir solutions as my example, since of course those are the ones that I'm able to talk about. Okay, so I don't know, I'm assuming you're somewhat familiar with Ophir. Some years back, we were acquired by Newport, and then some years later, we, together with Newport, became part of MKS Instruments. But we'll skip over that. So what I'd like to cover today is what you see here. We'll do a very, very brief overview of the basics. Our goal here is not to turn anyone into a measurement instrument design engineer, even though it's a cool thing to do, but just so that we're all on the same page and so that the rest of our discussion can have meaning. Then we'll talk about some items of passing interest, preventing laser damage to the measurement instruments that we're going to be putting into harm's way. Cooling of the sensors, keeping them clean, thermal offset. That's a bit of a not very well-known topic, but as you'll see, it could make a big difference sometimes. And some of the other issues that come up when using laser power meters to measure high power beams in industrial or similar applications, backscatter, implications of the need for minimizing footprint in these applications, and related to that, integration of the measurement instrument into a production floor environment. So let's begin with the beginning. An overview of the basics. As I said, a very, very brief overview of the basics. So the sort of applications where these very high power beams are used, and maybe until a couple of years ago, very high power maybe meant a couple of kilowatts. Now we're talking about many tens of kilowatts, and it's constantly increasing. So typical applications, okay, obviously research, but that's almost trivial. to a very large extent, we're talking about some type of materials processing, by which I mean brute force applications, using the power of a laser beam to burn, zap, vaporize, or otherwise process material. A lot of applications in the automotive industry, aircraft manufacture, shipbuilding, industrial components where we're, cutting, drilling huge pieces of material, or not so huge, but hard, other types of challenging characteristics. Processes like cutting, welding, cladding, drilling. Here you see an automotive production floor. We're going to be coming back to that towards the end of our discussion, which combines pretty much all of these processes. Here you see a jet engine turbine blade. I hope the resolution is enough that you can see the cooling holes that are drilled into that. Now, that would have been very difficult to manufacture using traditional mechanical production methods, but with the more modern laser-based processes, it's much easier. Still on the general overview of the basics, the way the sensors that we typically use for measuring and keeping track of these beams work is that they actually measure heat. So the absorbed laser beam gets turned into heat after it gets absorbed, and the heat flow through and out of the body of the sensor is proportional to the power in the beam, and it gets measured. Here you see a typical disc, which is the heart of a thermal type laser power sensor. The laser beam in this image would be coming towards you from behind the plane of your screen. We're looking at the inner surface of the disc that's inside the body of the sensor. You can see the thermopile ring over there. So the heat would get absorbed on the other side of the disc, somewhere in the middle of the aperture, and it spreads radially outwards as it makes its way out to the surrounding air, and that heat flow gets measured by the thermopile. Here's what it would look like in the sensor itself. Okay, you've got the absorber there, the beam enters into the aperture, the heat spreads through the disc which is inside that sensor, and then using various methods depending on all the details, the heat gets removed from the sensor. It has to get removed from the sensor at least as fast as it's coming in. Otherwise, the heat's going to build up, the temperature is going to start rising inside the sensor, and eventually something in there is going to fail. We'll look at the failure mechanism in a couple of minutes. There are, by the way, tricks by which we can sometimes get around this limitation, and we'll see shortly how that works. So here you see a few typical high-power sensors. Here's a water-cooled sensor for measuring up to 20 kilowatts. That module that you see on the right side there is basically a safety mechanism. Some sensors have it, some don't, obviously. That's connected to an interlock so that if it detects some sort of a failure in the cooling system, it can be set up to instantly turn off the laser to avoid destroying the sensor. Here in the middle, you see a sensor that measures up to 150 kilowatts. Just to give you a sense of scale, that one, it's 50 by 50 centimeters. It's not very big, sits on the desktop. And just for completeness, sorry, the sensor will normally work with a meter, sometimes referred to as a display. Every manufacturer has their own terminology, and the meter is how the user would interact with the measuring instrument, controlling the various parameters, wavelength settings, scales, and so on, and of course, seeing the output. Okay, that was our very brief overview of the basics. There are many ways to destroy or damage a measurement instrument of any kind, including a laser power sensor. We're going to talk about two in particular that are relevant to laser power sensors, and that is the power density being too high and the power being too high. So let's begin with power density being too high. So that relates to one of the main parameters that are listed in any laser sensor's data sheet, and that's what's usually referred to as the damage threshold. And by that I mean the maximum average power density, usually in kilowatts per square centimeter, the power incident per unit area And so the damage threshold is the maximum power density that a given sensor, or to be more specific, a given sensor's absorber can handle without damage. I should add that for pulsed beams, the maximum pulse energy density is also a type of damage threshold. To keep things simple here, we'll just keep referring to the maximum power density damage threshold. I should mention that we always, in Ophir data sheets, we always recommend having a safety margin in place. There are always tolerances in the laser, in the sensor, and so on. So our recommendation is always to try and stay below 50% of any given sensor's specified damage threshold as a safety margin. Now, a very important thing to be aware of, and many people, including seasoned laser professionals, don't always know this, is that the damage threshold is not just one number, so and so many kilowatts per square centimeter, but it depends, among other things, on the power that we're talking about. At higher powers, the damage threshold for the same absorber is going to be lower than at lower powers. Let me explain. Here, our x-axis is the absorber, the y-axis is the temperature. All right, so here we have a given absorber, and we have a low power beam coming in. So the low power beam comes in at the point of absorption. It's somewhat hot over there because optical power is constantly coming in and getting absorbed and getting converted into heat. And that heat starts propagating outwards in all directions through the body of that disk, through the material. So some distance away from that point of absorption, the temperature is already less hot. And as we get farther away, it's somewhat warm and so on. Because the overall power that's coming in is not so high, the overall area on the absorber is not so terribly hot, and so the heat that's continuously being generated has a relatively easy time moving away. Now here you see a screenshot from the simulation, the thermal simulation software that our engineers use here at Ophir to design these things. And you can see, obviously, red means hot, blue means cold. So you can see there's a relatively hot, small region right around where the beam is being absorbed. And even a small distance away from that, the temperature of the absorber material is already dropping down pretty significantly. Now let's take that same absorber, but now let's expose it to a high power beam. So the spot where the beam is getting absorbed is not somewhat hot, it's really hot. And instead of having a small area around it that's very warm, we have a large area around it that's still really hot. And only when you move very far away is it even beginning to become merely somewhat hot. Same absorber, same material, but you can see that the heat behavior is very different because the heat that's continuously being generated by the ongoing absorption of the beam has a much harder time moving out of the way because it's in a very crowded room. So it's going to take way fewer kilowatts per square centimeter to raise the temperature of that absorber up to the temperature where it's going to actually start burning or getting damaged. So at higher powers, that same absorber will damage more easily than at lower powers. That's something important to be aware of. So Ophir sensor data sheets actually reflect this. We always specify the damage threshold for any given sensor at the maximum power for which that sensor is rated. Since if you're checking out the specs of a 20 kilowatt sensor, then telling you the damage threshold at 10 watts might make for a nicer looking data sheet, but that information isn't really going to be helping you very much. As we just explained, with high power beams, the damage threshold is significantly lower than it is for the same absorber at lower powers. So for high power sensors, which is what we're talking about, where this is going to be that much more of a concern, we want to keep the power density as low as we can, which we do by this trick, whereby which we enlarge the beam before it actually reaches the absorber. So here you see a 10 kilowatt sensor. I hope you can see at in the aperture of that sensor, there's a gold-coated reflective cone. And what we do here, I wish we could claim credit for this, but this trick is pretty much standard practice in our industry. instead of the absorber just being, a flat surface on which the beam is incident, and then we have those limitations of the damage threshold being pretty low because we're talking about high powers, what we do is we have the absorber as a vertical cylindrical wall around that reflective cone. And the reflective cone is where previously the absorber would have been for lower power sensors. Now the beam comes in, and instead of hitting the absorber, it first hits this reflective cone and gets deflected radially outward, spread around a full 360 degrees with a divergence angle. So the power density that's actually reaching the absorber, the cylindrical vertical wall around that cone, the power density has been significantly reduced from what it was when the beam was originally coming in, and that allows the sensor to handle higher power densities than it otherwise would have. Now, very important tip to be aware of in this regard is that it's super important to be careful about your beam alignment. Now, everything that I just described about what that cone does assumes that the beam is nicely centered over the tip of the cone so that it really is being reflected in a complete circle, 360 degrees with a divergence angle, so that any given spot on that cylindrical absorber is actually seeing a reduced power density, and it can survive the experience and keep on doing its work. But let's consider for a second what happens if my beam is not properly centered, not properly aligned on the tip of the cone. Instead of being deflected in a full 360 degrees with a divergence angle, it's only going in one direction, which means that beam is being spread out over much less surface area than I might have thought, which means that that surface area that is getting the beam is getting a much higher power density than it's supposed to. And here you can see one of the possible results of that. When we get a sensor in for repair that's been damaged, and we see one of these reflective cone type sensors, and we see burn marks in specific areas, we're pretty sure that that is what had been going on there. Localized damage because one region of that cylindrical absorber wall was getting all of the power, which means much higher power density than it was supposed to be getting. This is actually expressed in Ophir's data sheets. Here you can just see an example. I don't know if you can read what it says there, but we mention here that that the damage threshold that we specified there assumes a circular beam that's centered on the middle of the aperture on the cone. It has to be centered to within plus minus whatever. I also can't read what it says here, but you get the idea. So that's something that we do point out actually in block letters in the data sheet. So that's preventing laser damage due to power density being too high. Now let's consider what happens when the power is too high. The power density being too high, you can have power that's way lower than the maximum and you'd think everything's okay, but if all that power gets focused into a small spot, then just as that beam might be used for cutting, drilling, welding a workpiece, you could end up cutting, welding, drilling your sensor, which you don't want to do. But let's now consider what happens if the power is too high. So if the power, the power being too high is going to overload the sensor. As I said earlier, the sensor is going to heat up more than it's designed to be able to heat up. And as the temperature in there rises, one of two things often happens. One is that the sensor's readout suddenly drops down to 0 and remains there. Sometimes it drops down to 0 but doesn't remain there. Sometimes it goes back to looking okay if we turn everything off and try again a few minutes later, but then shortly thereafter it again drops down to 0. That's a nightmare. As anyone who's dealt with troubleshooting knows, problems that sometimes happen and sometimes don't, intermittent problems, are much harder to solve because they're obviously elusive. once you can turn a problem on and off, then you've pretty much nailed it. So this sudden sensor death is one type of problem, one symptom, and there's a similar but different symptom. Let's hope this video works here, where instead of suddenly the reading dropping down to 0, what sometimes happens is that the reading suddenly starts going crazy and it becomes unstable. It doesn't go to 0, but it drops down and then goes back up and then stays somewhere and then drops down some more. You get the idea. So that can be pretty mysterious. So basically, when you have overheating of the disk, the first point of failure is generally going to be that solder connection from which the leads emerge from the sensor to the rest of the instrument. A possible mode of failure might be the connections in the thermal pile itself coming apart, but that usually would happen at a much higher temperature than the solder connections of the leads. Now, sometimes the overheating can be bad enough that the solder connection completely breaks, and then you've got sudden sensor death, the drop down to 0. Sometimes it becomes unstable. It might disconnect, but only partially, and then when the sensor cools down, it reconnects, only to disconnect again when it heats back up again with the next exposure to laser power. So the disease is the same, the symptoms might look a little bit different. Failure mode 1, the solder joint melting and disconnecting, is going to bring about that what I called instant sensor death, disconnecting and remaining disconnected. Failure mode 2 can sometimes lead to intermittent failure. Under laser exposure, the disk heats up and the solder joint disconnects, but then it reconnects when the disk cools back down, and so on. Or it could just become unstable and maybe disconnect, maybe reconnect, maybe partially disconnect, and then you get that weird erratic behavior that we saw in that video clip that actually was sent by a customer who was experiencing that problem. Now, usually most users probably know what their sensor's maximum rated power is. So you might be asking yourself, well, how would this happen? If I bought a 10 kilowatt sensor, I'm not going to expose it to 20 kilowatts. I kind of know that. So how might this happen? So let's imagine that I'm coming in to do a measurement, and I sit down, everything is connected, my laser is connected, the cooling water system is connected to the laser, my sensor is in place, everything is fine. And then, okay, I'm ready to start measuring. I turn on the laser and I turn around and press the button to turn on the cooling water circulation system. And then I turn back to my power meter and nothing's happening. If I'm talking about 10 or 20 or 30 or several tens more of kilowatts, that half a second between turning on my laser and turning on my cooling system could absolutely be enough to have destroyed my disk, to have destroyed my sensor. It doesn't take much at these sort of powers. So what we absolutely recommend as I was going to say best practice, but it's more than a best practice. It's a highly recommended practice, is that the cooling water flow should be up and running and steady before you turn on your laser. Because again, that half a second, if you turn on that laser even briefly, and just immediately then you turn and flick on press the button to turn on the cooling water, that half a second could easily be enough to have caused the damage already. And the water flow should be according to the specifications of the sensor. We're going to come back to those specifications shortly. So a highly recommended best practice that's related to this is not only make sure that the cooling water flow is on before you turn on your laser, but when you do turn on your laser, we recommend that you increase the laser power gradually. If the sensor is nice and healthy and everything is fine, then going from 0 to 30 kilowatts shouldn't be a problem if the sensor is designed for measuring 30 kilowatts. But if the sensor has even somewhat been exposed at some point in its past to a problem and that solder connection has been weakened, even if it hasn't been disconnected, then a sudden jump from 0 to a very high power might push it over the edge. So we recommend increasing the laser power gradually after you've turned on the cooling water flow, obviously. Those sudden jumps in power can cause mechanical stress, which could lead to disconnect, particularly if that solder connection has already been weakened, as I said, at some point in its past, but not necessarily so. Okay, so we've mentioned cooling enough times. Let's just say a few words about that. Generally speaking, we're talking about water cooling for these kinds of powers, tens of kilowatts. Fan cooling, I mean, in theory, one could build a fan-cooled sensor for tens of kilowatts, but the fan would kind of be like a jet engine, and we probably don't want that. So we're talking about water cooling. There are two main configurations of water-cooled sensors. One is the basic thermopile type that we already saw. Okay, they generally look like this, and you can see the water connectors there. That's an Ophir 5 kilowatt sensor, and the cooling water flows inside the body of the sensor usually around channels that are built into the sides of the disc that's inside the sensor, the sensing element itself, and the cooling water obviously removes the heat from the sensor. There's another type of water-cooled sensor, and that operates on a similar but not exactly identical principle, and those are what we call calorimetric sensors. Calorimetric sensors, by that I mean that the cooling water not only removes heat, but it's actually part of the measurement process itself. We're going to talk about that in a touch more detail in about a minute. But before we do that, there's a few important pointers about the cooling water that I want to mention. And by the way, remember this calorimetric thing, because we're going to be coming back to this also shortly. Here we see some typical sensors, again, these are Ophir sensors, of course, a 15 kilowatt sensor, in this case, with a target painted protective cover that protects the sensor when it's not actually measuring, and that target makes the alignment much easier. Here's a 20 kilowatt sensor with that same interlock module that we saw earlier, and here's a 30 kilowatt sensor. You notice that these sensors are getting more and more massive as we're talking about higher powers, because you want to be able to handle those higher powers and the water flow, et cetera, et cetera. And by the way, we're soon going to see a trick for getting around that, but let's not jump ahead of ourselves. Okay, so just a few things about the cooling water, because these are questions that come up all the time. We're very often asked, do we recommend a particular water type? Usually people are asking whether they can use tap water or should they use deionized water. DI water often has a bit of a bad reputation when it comes to issues of corrosion. Sometimes because the cooling water passes through the sensor as well as the laser and perhaps other components along the circuit, you've got various ions mixing in the water, and you've got heat and all sorts of other physical phenomena. And sometimes people find that either the cooling channels of the laser or the cooling channels of the sensor get corroded after time. And there are expert consultants out there that earn their living by helping deal with corrosion issues, because there's a lot of chemistry. It takes there's a lot of things that can go on there. So we actually have done quite a bit of work studying this. DI water generally is our recommended water type, as long as the pH of the water is kept neutral. When the pH of the water becomes slightly acidic, that's when you start getting into trouble, because then ions get leached out of the different metals that the water comes into contact with along its path, and then you can start having problems. Tap water can sometimes work also. It really depends on what's in the water in your particular region. In our specifications, we always list the recommended and the maximum and the minimum flow rate of the water, and the temperature range of the water, and the pressure drop across the water tubes in that cooling system. These are all things that are listed there. Very important is not only the absolute temperature and flow rate of the water, but more important than those are the stability of the temperature and of the flow rate. A slight change in the temperature of the water or its flow rate can lead to a slight change in the temperature of the sensor because the cooling effect changes. The rate at which heat's being removed can slightly fluctuate, and these thermal sensors can generally pick up a change of 1 degree Celsius in a minute. That's how sensitive they are. So as far as possible, you want to keep the temperature and flow rate of the cooling water circulation stable. Very often one is going to want to put in some kind of a ballast tank there to take up the slack and keep and eliminate fluctuations that might be coming from the circulator itself. Another question we're often asked is the cooling capacity that we recommend. So in general, we don't recommend any particular water circulation system because all we're interested in as far as the sensor goes is that heat is being taken out at least as fast as it's coming in. So if you're going to be working with a 30 kilowatt beam, you want a cooling system that can remove heat at a rate of at least 30 kilowatts. That's more or less all that the sensor is interested in. I mentioned corrosion. I should just mention that Ophir offers a corrosion-proof sensor in which only copper and non-metallic materials come in contact with water. So if you have had issues with corrosion, then feel free to speak to us about that. Still on the topic of the cooling water, I mentioned earlier, I'm just going to mention it again now. Where possible, it's a good idea to have an interlock module so that it can disable the laser if it senses a sudden rise in temperature of the sensor, which is an indicator that something has gone wrong with the cooling system, and that could absolutely save the life of your sensor. As I mentioned already several times, you want to turn on the cooling water before you turn on the laser. I can't say that enough times. I just threw out a whole lot of information for a very detailed guide to the best use of water cooling. We have a white paper on our website. It has the very useful and functional title, How to Use Water-Cooled Ophir Sensors. The information there is absolutely relevant not only for Ophir sensors. The specifications obviously refer to Ophir sensors, but the information there is very helpful generically. You can find that if you go onto the Ophir website in the resources section at the bottom of every water-cooled sensors webpage under technical notes, or just search for it in the search window at the top of every webpage on our website. Again, How to Use Water-Cooled Ophir Sensors. I think you'll remember that name. Okay, you remember this? I mentioned calorimetric. So some sensor types are calorimetric rather than based on a regular radial thermopile. What happens there is that instead of measuring the heat flow radially outward from the point of absorption past the thermopile, what happens in a calorimetric sensor is that the sensor measures the temperature increase of the water, which obviously is a function of the power of the beam coming in, and it measures the flow rate of the water. And those two pieces of information combined enable the sensor to then derive the power that was coming in. So here you see some examples of calorimetric type Ophir sensors. There's water flow. There's a water flow sensor in the water channel that measures the flow rate of the water. And obviously there's a temperature sensor. Well, there's actually two temperature sensors, one that measures the temperature of the cooling water coming in, and the other one that measures the temperature of the cooling water going back out. So we know the temperature difference between those two. So we know the temperature increase and we know the flow rate. Very, very important tip. When you're done with your measurement and you're putting the sensor away, obviously you're going to want to drain the water out. Otherwise, you don't want to just leave the water in there for a long time because that could lead to mineral deposit buildup as the water dries. So you're going to pour the water out, and you probably don't want to leave drops of water sitting in there. So you're going to want to purge the channels of any leftover water. Do not use, I'm saying it as emphatically as I am because we've learned this the hard way, okay, through a lot of bitter experience. Do not use pressurized air to purge the channels of any last bits of water residue. I'm being gentle here by saying that it could damage the flow sensor. The truth is it will damage the flow sensor. Water in the sensor should only be removed by tilting and turning the sensor and letting it drip out, and there isn't really much of a shortcut. Okay. Another very helpful tip is keep your sensor clean. Particularly when we're talking about the sort of high-power industrial applications where there's a lot of process debris flying around, and that could settle onto the sensor's absorber surface. So as they say, sort of, a milliwatt of prevention is worth a kilowatt of repair or something like that. So if you get such process debris splashed onto your sensor, clean it off. Usually a soft tissue with a suitable cleaning agent. In some cases, depending on the sensor type, no cleaning agent and no soft tissue or anything, just clean air blow. Those reflective cone sensors are like that. You don't want to touch those cones because the reflective coating is somewhat delicate. Check with the manufacturer for cleaning instructions and follow them. Here you see a thermal sensor with what most likely started off as some kind of organic debris that splashed onto the sensor. Now, it would have been very easy to clean that off with a soft tissue and a cleaning agent, ethanol, acetone, something like that, and it would have been easy, but it wasn't cleaned off, and the next exposure to laser power burned that stuff on. There's no way to clean that off anymore. That sensor needs a relatively expensive disc replacement, and that's unfortunate. So again, one should try to keep the sensor clean rather than figure out what to do about the fact that it wasn't kept clean. For some of our sensor models at Ophir, the high power industrial application type sensors, we offer this accessory. It's a remotely actuated shutter-based protective housing so that when the process is happening and the sensor is not measuring, it's covered. And only when the process is not happening and we're taking a measurement, I guess, typically before the next workpiece is put into place, then the shutter is remotely opened, the measurement is done, and then it's closed again. That's just an example of prevention being much better than repair. Okay, thermal offset. This is a bit subtle, but not as subtle as it might sound at first. Ophir power sensors, well, the meters have always, an offset function. The button is on the meter, but it refers to the sensor. And the idea of that offset button is to remove any kind of optical or thermal offset. For example, background light. Constant background light, we want to remove it from all subsequent measurements. So we press the offset button before turning the laser on. Before turning the laser on, we were measuring some kind of a DC power level because of that background light. We press the offset button, and that value gets subtracted from all subsequent measurements. So as soon as we press the offset button, we're going to see 0 on the meter, and then we turn on our laser and carry on with our work. It's important to use that offset button to 0 the sensor's background offset only when the sensor is in thermal equilibrium with its environment. For example, let's say you bring the sensor in from a hot car into an air-conditioned lab. You connect it to a meter, you turn on, even before you turn on your laser, you look at the meter and you're going to see a reading. Actually, you're going to see most likely a negative reading, because the sensor is hotter than its environment. So heat is now moving from inside the sensor outwards into the surrounding air. And that heat flow is going to be picked up by the sensing element on the disk. It has no way of knowing whether heat flow that it senses is from incoming laser power or outgoing heat that came from the sun out in the hot parking lot. So you might be tempted to press the offset button so that you'll see 0 instead of that reading and start doing your work. That would be a mistake. Why? Because as the sensor cools and approaches thermal equilibrium with its environment, that heat flow is going to drop down and eventually it's going to stabilize at 0. But because you press that offset button, it's going to continue subtracting that original offset from all subsequent measurements until you tell it to stop. So that offset subtraction that you started, which might have given a correct 0 reading when you first pressed the button, is going to become increasingly wrong as the sensor cools and approaches thermal equilibrium with the air-conditioned lab. So you want to wait until the sensor reaches thermal equilibrium with its environment, no shortcuts again, and only then, if you have a DC optical or thermal offset, a background light or a heat source nearby that's constant, then you press the offset and you're going to remove that offset, which is now going to be a correct thing to do. I should just mention that the offset caused by the heating of the sensor when the beam is on, you're measuring laser power for hours at a time, the sensor gets kind of hot, so it's radiating heat out into the room, but that's laser beam generated offset, and that's built into our calibration without getting into all the gory details. So if the sensor was in thermal equilibrium with the room, and then you started measuring laser power, so the only heating that took place was because of the laser, then the offset that you pressed at the beginning before you turned on the laser is bad offset that you're going to correctly continue to 0. So that's an important thing to keep in mind, and is generally not so well known, even among seasoned laser professionals. Moving right along. Let's just say a few words about backscatter. Typical laser sensor absorbers have absorption on the order of 90-something%, and the other 10, 5, 10, whatever percent, the number also depends on wavelength, gets reflected back. Usually the absorbers have a matte surface, which means that backscatter is diffuse. But when we're talking about tens of kilowatts, that's still a good couple kilowatts that are being backscattered back out into the room. Okay, diffusely, that's true, but still. So we offer at Ophir, and I imagine other manufacturers have something similar, a scatter shield as an optional accessory. And basically, I apologize for my artistic skills here, but I hope it gets the point across. What basically happens is you attach it to the surface in front of the aperture, and then the beam comes in, those 5 or 10 or whatever percent of the power gets diffusely back reflected out. Much of that meets the inner surface of that scatter shield, and much of that gets reflected back into the aperture of the sensor for a second go. So instead of 10% being reflected, usually something like, I know that with the Ophir scatter shield, something like 70% of that backscattered power ends up getting reabsorbed. So we're significantly cutting down the backscatter. Obviously, for the same power, the sensor is going to be absorbing more, which means that the meter is going to need to know, quote unquote, that the scatter shield has been added. There needs to be a separate calibration factor for the scatter shield in condition to make sure that the reading is correct, even though much more of that beam is in fact being absorbed. Okay, footprint. You remember in our opening slide, we saw an image of an automotive manufacturing floor. Measure the real estate there, it's prime real estate. Any measurement devices that are in there need to take up as little space of that floor as possible. So in these kind of industrial applications, footprint can really be an important limiting factor. So at Ophir, we have a trick that we developed. I don't know, I assume that some of the manufacturers might have something similar, but whereby we can use small sensors that normally are meant for much lower powers to measure high power beams without having to be huge and bulky and whatever. How do we do this? So there are some tricks that we employ to be able to measure high power lasers without needing large, heavy, expensive water-cooled equipment. And this involves what at Ophir, at least, we call pulsed power mode. The basic idea is that these thermal sensors, besides being able to measure average power of a continuous or a repetitively pulsed beam, can also be used to measure the energy of one single pulse. The time constant of these sensors is on the order of seconds. So if you're pulsing at a few hertz, the sensor has no way of knowing that it's even pulsed. It thinks it's just a CW beam, at best, maybe with a bit of ripple. But a single pulse, it can absolutely, yes, measure the energy of that pulse. I won't get into how it does that right now. But what we do is we fire this high power laser for a short, precisely known, precisely controlled time. And we treat that short exposure as what we call a single shot pulse, and we measure its energy. The sensor can do that. It might take those few seconds of response time to finish doing that, but that's fine, irrespective of how short the pulse was. And since we precisely knew the duration of that pulse, because we just said a short, precisely controlled time, so we can divide the measured energy by the known time. Energy per time is power. So we thereby get to measure the power, but the exposure of the sensor to that high power was short enough that the total amount of heat that got in there wasn't so high. Of course, we still need to give the sensor time to physically cool down, but that's fine. In many applications, that's perfectly okay. We take a measurement, and then we start on the next workpiece, and it may be many minutes before we need to take another measurement. Perfect. So now, dividing the measured energy by the known time can be done in a few ways. Obviously, if you did it manually, you know the time. You can take out your calculator. Nobody has a calculator anymore, but we all have a smartphone and divide the measured energy by the time. Okay, obviously that's a bit trivial, but we can do this semi-automatically, whereby we know the pulse duration, the pulse width as we call it, and we can have a meter that prompts us to enter that known exposure time. It will measure the energy. It'll ask us to input the time, and it'll do the math for us. I'm going to refer to that as semi-automatic. We have a bunch actually of Ophir meters that have that function, that mode built in. Or it can be done automatically, and we're going to see in a moment that we have some instruments that have a fast photodetector built in, and the instrument automatically measures the exposure time as well as the energy and doesn't have to prompt the user for anything. So let's look at that now. So I had mentioned that we're going to see some applications where this trick comes in handy. So this is basically the sort of application that I'm referring to. You remember that automotive manufacturing floor. So clearly in a production floor environment, one is not going to use a handheld instrument that requires a human operator to come in and press buttons and read a display on a screen. That's not how these things work. So for such applications, the ideal solution is to use instruments that are integrated into the factory floor network. Here you see some examples of Ophir devices. These use short pulse exposure, as we just described. So there's no need for water cooling. So the instrument is small. This is, I don't know if you can get a sense of the scale here, but it's a little bit bigger than a human hand. This particular device measures up to 12 kilowatts, and it communicates with the factory floor network with the server that controls it using various standard industrial protocols, as you can see from the different connector types. There's a remotely controlled protective cover, so it opens up when we want to take a measurement, and then it closes, and the process on the next workpiece begins. Okay, so in summary, we talked about very briefly about the basics. We talked about preventing laser damage, and I'll just mention again, turn on the water flow and bring it up to speed before you turn on your laser. Bring the laser power up gradually. Watch the cooling water flow specs that the manufacturer gives for what the sensor needs. keep the sensor clean, much better than having to have it repaired. And then we mentioned a few other topics, the thermal offset, wait till the sensor's in thermal equilibrium with its environment. There's no shortcuts. Optional accessories for reducing backscatter where that's an issue. And we saw some solutions. We looked at Ophir solutions, but these are pretty typical in the industry for enabling devices to be small footprint, not needing water cooling, perfect for production floor integration in these kind of industrial high power applications. Okay, so that's what I wanted to get across. I hope that's helpful. And Justine, back to you.
Great, thank you so much. And now let's move into the Q&A. As I mentioned earlier, if you'd like to submit a question, just use that Ask a Question box. And there are some in here already, which is great. So let's just jump right in. Let's see, I'm seeing fluctuations in the power reading from my water-cooled sensor. How can I know whether it's coming from the sensor or not?
Okay, that's interesting. Okay, so if the setup and the water cooling are all stable, and obviously you want to make sure that they are, but if they're stable, then there's no reason, as far as the sensor is concerned, that the reading should show any kind of significant fluctuations. Simple way to diagnose this is just try putting a photodiode in front of the sensor so that it's looking at the absorber and seeing a little bit of the back reflected power from the sensor's absorber. The photodiode has obviously a fast response time, unlike the sensor. So looking at the output signal from the photodiode, you'll see if the power is actually fluctuating, because if the power is steady, then you'll know that the fluctuations are, for some reason, coming from the sensor, and then we'd need to look into that.
Okay. What is the maximum water pressure I can use with Ophir sensors?
So that depends on the sensor. We usually have that in the specifications. I don't actually remember what typical numbers are like, because I don't have the thing in front of me, but the specification. But if you first of all, each sensor specification should have that number. You know what? Yeah, I think it does. But even if it doesn't, then that article that I mentioned earlier, how to use Ophir water-cooled sensors, as a whole table. And again, I just don't have it in front of me, so I can't say any actual numbers. But there's a whole table there of the pressure drop for different flow rates and how those relate to different power levels. So that information is always there. It's just not in my head.
Okay. How do you compare the thermopile to the integrating sphere, and what are the pros and cons?
Okay, an integrating sphere, for those of you who aren't familiar with that, is basically a hollow sphere, the inside of which is white, diffuse, and highly reflective, either a coating or an insert. And when a beam of light comes in through an open part of the sphere, it bounces around in all directions an infinite number of times, quote unquote, so that it gets uniformly distributed throughout the inside of the sphere. And then we've got a sensor, like a detector, built in. And the detector obviously sees only a small bit of the total power that came in. We'll use these. It's kind of like you want to think of a diffuser in 3 dimensions. So we can use this as an accessory to capture widely diverging beams, or we can use this even for collimated beams, where if, let's say, for example, if it's high power but changing quickly, so we want to use a photodiode because it's fast enough, but photodiode would get saturated. So this is a way of, there's all sorts of different applications where we might want to use an integrating sphere. So the integrating sphere is basically an accessory. So it's not an integrating sphere or a thermopile sensor. It's at Ophir, actually, we don't have any integrating spheres that have built-in thermopiles. We have lots of integrating spheres with built-in integrated calibrated photodiode sensors, but there's no reason in principle that it can't be done also with the thermopile. I think other manufacturers actually do have that. So the integrating sphere would be used specifically when you need one. There are capabilities that it gives you, such as I said, capturing a widely diverging beam, or having an inherent kind of attenuating effect when you want to use that. I will mention that there are some applications where it might introduce problems of its own. For example, LiDAR, talk about the laser diodes with very short pulses that are used in, let's say, automotive range-finding applications. Those pulses can be a few nanoseconds long, and you take an integrating sphere with an inner diameter of even a couple centimeters, you can do the math. You're going to be, it'll take quite a few nanoseconds for the light to bounce around, and you're going to be stretching that pulse, which is going to interfere with some of the measurement. So there's always pluses and minuses, but in general, it's not this or that. The integrating sphere, as I see it at least, it's an accessory that you can use to add capability to a given detector type, let's say.
For water-cooled sensors, the specifications say the temperature of the cooling water should be in the range of 18 to 30 degrees Celsius. Tap water is usually colder in our country. Is it okay to use water that is colder than the specified range?
Yes, I remember right. I think in Scandinavia, many countries in the northern parts of the world, that's definitely an issue. So on the one hand, as I said, much more important than the actual temperature of the water is the stability of the temperature. However, having said that, there is a reason that we want to limit the temperature range. Now, there's no question, the 18 to 30, we do state that, but that's like a good rule of thumb. In practice, the water can certainly be significantly colder or sort of significantly warmer. If it's significantly warmer than 30, then you're probably going to be limiting the maximum power to significantly less than the sensor's rated for. But in the case of the water being too cold, which is what the question is, there are two possible concerns. One is that if the sensor is cold enough, there might be water, and the air is humid enough, then there might be water condensation forming on the absorber surface, which may or may not be a problem, but it's something to think about. A little bit more subtle is that there might be an offset, a thermal offset caused by the difference between the ambient room temperature and the temperature of the sensor. The sensor is going to see, quote unquote, two different temperatures. It's going to have the temperature of the cooling water flowing inside it and the temperature of the room air around it. Now, if that temperature difference is small, as it usually is, then its effect on the heat flow inside the sensor will pretty much be negligible. But if it's a large difference, then there will be some level of heat flow between the cold sensor and the warmer air. And this could result in some level of offset in the reading again, because there's going to be a heat flow that the sensor thinks is because of incoming laser power. And these sensors are, in essence, physically measuring heat flow.
All right. The sensor specification sheet states that power accuracy is plus or minus 5% or 3% for lower power sensors. What exactly does that mean?
Okay, so the power, all right, this is a big topic, but basically the power accuracy of plus minus 5%, let's say, refers to the absolute uncertainty of the measured value with reference to NIST. All of the calibrations are traceable to NIST. Excuse me. So for example, if you have a 1 kilowatt reading, and the sensor's specified accuracy is plus minus 5%, that means that the actual true quote unquote power value would be somewhere between 0.95 kilowatts or 1.05 kilowatts, 5% above or below that 1 kilowatt measurement. And then to this, you might need to add other uncertainties if they exist. Usually the data sheet gives additional uncertainty with this or with that or whatever. I should just add 2 points, side points, that since whoever's asking this is obviously very familiar with these QA issues. So one, this assumes that the reading is from around 5% of full scale and up. If you're measuring right near the floor of a given scale, a given range of a sensor, you might start getting into linearity issues and your accuracy is going to be affected. And two, I should just point out that our accuracy specification is based on, our specifications are based on a 2 sigma standard deviation. If anybody doesn't know what on earth I just said, then don't worry, but whoever asked that question obviously does. So I just have to mention that again for completeness.
Okay, well, we are just about out of time. Any questions that we weren't able to get to today will be addressed directly later via email. And don't forget to take our exit survey that will pop up as soon as we're done here. Your feedback is really valuable and it helps us to continue creating and offering engaging content. So, on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Mark Slutzki for a great presentation, MKS Ophir for sponsoring today's webinar, and of course, all of you too for joining us. Enjoy the rest of your day.
Thank you, everybody. Bye-bye.